seconds. All right. So let's start. Uh, how was your spring break? Good. Good. That's awesome. Let me start with the some announcements. So there's a small follow-up on the one. There's a slight change in the grading policy. It's short answer 1 to 4. So I downgraded a little bit with the. You guys remember to bring the mid? No.
Nope.
Nope. All right.
Totally forgot. I
Okay.
can go with it after you're done.
Yeah, sure. So you should take a look at the short answer 1 to 4, and then if you omitted and -1 as a multiplier, there should be some downgrades. But I basically changed the grading policy to not to downgrade the question for that. Does that make sense? Yeah. So please bring the midterm to me if your grade is impacted by the change, so I can correct the midterm score. Okay. Does that make sense? Yeah. So please take a look at short answer 1 to 4 and see if your grade is impacted. And then if it is, you should bring down. Good. Any questions? All right. And then the second announcement is about changing the course schedule. So basically, we're moving all the same topics up by 1 lecture. So next lecture will be about limited Eigen variable, and the Thursday's one will be about logit, and et cetera, et cetera. And the midterm date will be unchanged. So all of this changes about giving you more time to give you feedback on the relevant problem sets before the second midterm. So before the change, there was no time to give feedback on your problem set for instrument variables before the second midterm. Instrument variable is the last topic for the second midterm. But then before the change, there was no time to give you feedback on the problem set. But now you have more time to think more about the topic. Does it make sense? So basically, all of the topics are moving up by 1 lecture. That's all. Yeah. And then the midterm date will be unchanged, and the instrumental variables will be covered for the second midterm, but not after that. And instead, there will be 1 panel model lecture after the second midterm. Yeah. Any questions? Yeah.
You might have addressed this in lecture, but I wasn't there. Is it cumulative? The
final?
No, the next midterm.
Only the final is the
Only the final. Okay. Sounds good.
Any other questions? All right. So for today's section, we'll talk about HLM, hierarchical linear model. So it is also known as multi-level model or mixed effect model. It has different names, but these 3 are the most popular ones. So note that mixed effects model includes nonlinear multi-level models. So when you talk about multi-level model, it is typically assumed that it's a linear model. But for mixed effects model, you're expanding the term in terms of including nonlinear hierarchical models. Does that make sense? Yeah. I won't talk too much about nonlinear multi-level models, but it won't be covered in the lecture or something like that, exams or problem sets. But an example of this model is basically that if you if the data are nested within schools, but then if students switch schools or if they move on to different stages of educations, for example, from middle school to high school, then it's kind of hard to make the argument that the data are strictly nested within that specific school, because students can be nested within more than two groups, basically. Anyways, this is all FYI thing that won't be covered in the problem set or the exam. But the motivation is important. Motivation of hierarchical linear model is basically when you have clustered data, meaning that you have each individual, say, nested in schools or neighborhood or family or siblings or stuff like that. So it means that they share some sort of characteristics that might be observed or not observed characteristics. Good. And precisely because of that, they create clustered error structures, right? So as we covered in GLS, it creates correlated error structures, right? What does that, what kind of issues does that lead to? Oh, wait.
Is it heteroscedasticity?
Heteroscedasticity is a slightly distinct matter of correlated errors, actually. So what is the consequences of right, correlated errors? Anyone?
Are you looking about some estimation,
Uh-huh.
like the bias,
Bias in what? Sorry.
bias in the coefficient?
Actually-
The standard error.
Yeah, not in beta coefficient.
Right.
So beta coefficient will be still unbiased, but it'll be inefficient, and standard errors will be biased. Yeah, that's the consequences of having correlated error structures. Good. So, I'll give you an example. Let's say we are looking at the relationship between GPA, someone's GPA, and household income. Alright? So the dependent variable is GPA, a student's GPA, and the independent variable is someone's household income. Let's say we have this data, individual GPA is 175, 0.25, when these two students belong to family A. So household income is $20K. Annual household income is $20K. And household average will be 3.0. And we have another family that has this data, also we have these data. Okay. Okay. So, for each family, the students within each family, the students share household income, right? It means that did you all bring? Right. But even after you run the regression of GPA on household income, there could be some unobserved family characteristics, right? That'll make these errors correlated with each other. When we have 20K, this is 50K, and this is 70K. So these two students belong to family A. And these two students belong to family B. And these three students belong to family C. Good. So it means that by looking at one's error, you can easily figure out where, you can guess like where others' error would be within that family. It means positively correlated error in that case. Does that make sense? That's what correlation is, right? By looking at one's big error, you can guess what the direction of the other person's error will be. Good. So that's what it means by correlated, positively correlated errors. Good. This meets the problem of bias standard error because if you remember, OLS standard error estimator is estimated errors variance divided by n-1 multiplied by variance of x. Do you remember that or? Good. But then the problem is that this variance is obtained by IID assumption. And for variance of x, let me draw another graph. To calculate the variance of x or the degree of dispersion, you can, this is frequency, and there's 2 people at 20K, and there are 2 people at 50K, and there are 3 people in 70K. Good. So it means that, so it is basically precisely because they share household characteristics, household income, the variance of x is exactly same, regardless of whether this is 1, 1, 1. I mean, to be exact, it should be this one, but anyways. The variance of x will be exactly the same because the variance of x is how x is dispersed from each other. Does that make sense? Any questions about that, or am I making any sense so far here?
What does the lower chart mean?
Oh, what? Oh, so
That's really
regardless of, so let's forget this one. This one's variance and this one's variance is exactly the same.
What is the lower one?
This one?
Yeah.
20K, 50K. This one is when there is no quote unquote replication of the data, precisely because these students share household incomes. So let's say there is 1 student in each household. Yeah. So the variance will be exactly same for x variable because their distance from each other is same. Good. So this one is same. What about this one? And -1. It's exactly like you are replicating the same data set into, you're doubling or, replicating the same data set by 2. Because each student share the household characteristic, the household income, so they have same number for each data, for each individual. 20K, 20K, 30K, 50K, 50K, 70K, 70K. Does that make sense? So it means that even though variances of x is same, you are blowing up this n-1 problem part. Good. So it leads to underestimation of standard error by OLS. Good. So what would you do in this situation? You need to either adjust this error part. There is an error. That's robust standard error. Adjusting this part is robust standard error. Or you are using a different model or formula for this situation. That's multi-level model. Good. Any questions? Nope. And another motivation of HLM is to use more information on the group level. As we saw earlier, we can calculate the average of the students within each family, right? Family average, right? You can use that information to know more about how the family characteristics affect the average GPA for the family. So you can have more, use more utilize abundant information on the group level as well. Okay. So you're basically making a new variable out of family averages for GPA, and then you're trying to explain that variable as well. Good. Not just individual variances within that family. Good. And then, so what do you mean by cluster or group, right? So this is more of an FYI thing rather than just problem set or exam questions. But so there are contested opinions about what constitutes a group or a cluster, actually. So each cluster should consist of a random sample from a wider population. For example, from the wider population, you are randomly sampling families, and then you are randomly sampling individuals within that families. For schools example, you are randomly sampling schools, and you are sampling students within that sampled schools. That's what it means by clusters. So you're random sampling clusters first, and you are randomly sampling individuals within that clusters. You guys, are you guys familiar with the concept of cluster sampling? Yeah, that's why it's called clusters. So therefore, individual level characteristics are not people level. Categories of such variables are not a random sample from a wider population, but are based on a fixed classification system. Which for this sounds really complicated, but I'll give you an example. So we do not sample gender categories randomly. Right? We're not randomly sampling men or women and then sample individuals within that sampled category, right? We're not randomly choosing which if we should only sample women or men, and then sample individuals within that specific gender category, right? That's not what we're doing. Right? We sample both men and women, right? So categories of such variables are not a random sample from a wider population, meaning that gender cannot be a cluster in that case. It's not a group in that multi-level model terminology. Good. But there has a study that a bunch of people actually argued that the categories of an individual characteristic can be clusters if independent variables errors are correlated within categories. So as long as you have correlated error structures because of this shared characteristics for women versus men, for example, then it should be considered as a cluster. Okay. So there have been some contested as well. But again, this is just FYI. So let me talk about, let me delve into more detail of multi-level modeling. So the basic setup here is basically what it does is decomposing errors or the variance of errors into between group variance and within group variance. So the basic setup can be noted.
It's not coming.
Yeah. Oh, not sure it'll work or not, but yes, it works. Beta 0, EJ plus EJ, EIJ. Where Yij is the dependent variable of a unit I or individual I within group J. In beta 0 is the brand mean, of course. And Uj is group level error, and Eij is individual level error. I'll give an example. So let's revisit GPA example. So the grand mean of, which means the mean of all students' average GPAs is 3.0. And 3.0 is the family mean for family A, where there are 2 students in the family group that has this one. Then the average for the family A would be 3.0, which means that U1 hat will be 0. Why is that? So it means that you have this E11, this one, right? So you have this data, these data, right? And then you have other family members, other people from different family, right? You have these different data, right? And then you are decomposing the variance of these data into group averages and the other errors net of group averages. So group average was 3.4 or 3.0 for family A, right? You're calculating the group average and then calculate the EIJ after you subtract or subtract the data point from the group average. Does that make sense? And for this one, it would be 2.5 2, 5, 3 hat is. I'll explain why there's hats later, but you would have that. By the same way, you can calculate 1, 2. You have 2, 2. E1, 3. E2, 3. And E3, 3.
Why is that E tab 1, 2? I know it's positioned in the matrix.
So you're asking this one or hat?
Or yeah, the second.
Just one,
Yeah.
1, 2. So this is individual 1 from the family 2.
Oh, okay.
Yeah. Does that make sense? Yeah. So J here represents each family or group, and I is represents the person within that group. Good. And so the intuition here is we are constructing a new error term, Eij, after absorbing the group averages. Or the error term that represents the shared group characteristics. The variance of Y shared in group J. This is Uj. So you are constructing a new error term Eij, after absorbing Uj, which represents the variation of Y shared in group J. You're saying that, oh, the group average must be because of you're thinking that the averages must be the product of shared family characteristics. Good.
Do you mean after considering group level
Error. Yeah.
errors
Yeah.
and individual level errors can be independent?
We are assuming that. Yeah.
That table are that idea.
Right. Yeah.
Is that minus z? It's a glare, so I can't see.
No.
Is that 0? Is that E for 275 at the top?
E11.
E11
hat.
equals negative 0.
2.25.
Okay.
0.25. Yes. All right. So and this is a little bit tricky, but it's important. Please note that we treat Uj and Eij as random variables. So there is a hat right here because it's numbers. It's not a random variable. But then we are treating Uj as a random variable, meaning that U1 hat can change depending on the sample you draw. Good. Do you remember the difference between E and E hats? So E hat is obtained within that given a specific sample, and EI in regression model, OLS regression model, EI is a random variable that can vary depending on the sample you draw. Obviously, you can basically calculate the UJ hats, sorry, right, and be happy with it. But that's not the point here, right? The point here is to explain what's going on within these differences, and that's why we should consider it as a random variable. Good. And then consider them as consider UJ as a random variable is needed for calculating the standard errors for that group level variance in predicting group level variance. So obviously you can, depending on the interest, you can calculate all of the UJ hats, and be done with it. Like you don't have to try to explain the variance. Depending on the interest, only if you're really interested in this individual level variance, that is fine. But if you have interest in explaining the group level variance with group level characteristics, then you should let it as a random variable. Good. So there are a series of assumptions of HLE. Could you see that? Okay. Assumptions, yes. So these assumptions are all when there's no omitted variable bias. Let's assume that first. When there is no omitted variable bias, you need to make a series of assumptions. First of all, covariance between UJ and EIJ should be 0. Meaning there is no correlations among errors across levels. And second one, UJs are IID. Good. IID as normal distribution with the 0, the mean of 0, and the variance of tau. It's basically sigma for UJ. And EIJ is also IID, is assumed to be IID with the normal distribution with the mean of 0 and the standard deviation of sigma. So note that EIJ here is is the one net of group variance. So you're assuming that after you observe group variance or group averages, you are assuming IID after that. Good. How?
what?
Yeah.
Yeah. You mean the variance for UJ, right? Yeah. So did you say that like EIJ should be IID when conditioning on the
Oh,
group
EIJ
level
is by construction, it's net of UJ.
net of UJ, right?
I'm saying these assumptions because it is related to bias decomposition. That's which is the point I'm trying to make. Covariance of Yij here can be this one without any predictors. And V0 is a number, so we don't have to care about it, right? This leads to variance of Uj, variance of Eij, plus 2 covariance of Uj, Eij. But then it is assumed to be 0 here. Good. So therefore, Yij's, oh sorry, this is all variance, sorry. Variance of Yij can be decomposed into variance of Uj and variance of Eij. What it means is basically you are decomposing the variance of Yij here into group level variance and individual level variance. So, any questions? Nope. So by regression model, we're trying to explain either between group variance and within group variance, or both. Good. And note that this is actually related to the problem set question, but between group variance, Uj, variance of Uj, can be explained by both group level and individual level predictors. I'll give you an example. Let's say we are looking at SAT scores and the influence of schools' funding level on students' SAT scores. Okay. And which means that students are nested by each school, right? And so in that case, individual level characteristics can be, for example, parental income or students' socioeconomic background, family background, basically. And between level variance, Uj, which was about school's average, right, for SAT scores, right? They can be explained by parental income. Because a school's average can be higher, for example, by the over-representation of students from high socioeconomic background. Does that make sense? So individual level characteristics can explain uj as well as uij as well. Good. But for school level predictors, school level variables, independent variables, you can only explain UJ's variance, but not EIJ's variance. Why is that? Everyone has the same school fundings, right? For within each school, right? So within like EIJ, which represents the SAT score variance within that school, cannot be explained by school level predictors, precisely because they have exactly the same level of fundings for the school. Good. So this is so this is a little bit of getting ahead of myself. Do you have a question? Sorry.
Oh, he clarified.
Oh.
Clarified for me. Thank you. No, you're
Sure. I am getting a little bit of my ahead of myself. So don't worry about it if you don't really understand what's going on here. It will be covered almost at the end of the semester. But multi-level models, different name is mixed effects model because it's a mixture of fixed effects and random effects. Where fixed effects really represent the explained parts of UJ. So you're trying to explain the UJ, right? And then, for example, you're trying to explain schools, the variance of average SAT score for that. Does that make sense? Good? No? Good. So UJ is basically a school's average for SAT scores, right? And then you're trying to explain it with school's funding level. Good. And the explained parts of UJ is called fixed effects. And unexplained parts is called random effects. And multi-level model is also called mixed effects model, a mixed effects model, because you can explain parts of the various UJ and while letting it randomly vary. So you can have both fixed effects and random effects. Good. And you will hear this term fixed effects model when there is no random effects left. So you are explaining the whole variance, the exact amount of variance. You're nailing it down for exactly for group averages. So this is FYI, but this is possible if you add school dummies for all schools. It is possible to do that, right? if you include school dummies, then it will calculate the UJs exactly, estimate the UJs exactly, right? Good. Am I making any sense? Or if you find it really confusing, that's fine. It'll be covered later, so that's fine. But what I'm trying to say here is fixed effects model is a variant of multi-level model, or special case of random multi-level models. And random effects model is basically you are not really explaining UJ.
So the random effect comes from the only the variable as well.
So as long as you're not explaining away, explaining the exact variance of UJs, then you are still having random effects going on
Because of only variable.
for school. Yeah.
Also,
So it's mixed effects model because you can have a little bit of fixed effects and random effects going on. But if you're calling it as a fixed effect model, then you are explaining all of the variance of UJ, explaining away. And random effects model is basically you're not fixing it with the UJ. You're not explaining at all with the UJs. Good. Awesome. And we covered the concept of ICC, intra-class correlation. This is unexplained variance between group variance. This is divided by unexplained variance, or total variance. It is noted either as use sigma squared, unexplained UJ's variance, sigma, divided by UJ sigma plus EJ sigma, IJ sigma. To be consistent with the term that we used above, it is also noted as tau squared plus sigma squared. It is same thing. They are same things. So it is basically related to the purpose of multi-level models. If you don't really predict anything and then run the multi-level models without predictors, basically, then it'll show how much of the variance is coming from the group level averages. Good. So if ICC is really low, then you're saying that there's no point in using multi-level models, using a multi-level model, because there's no shared character, there's no variance of Y that is coming from the shared characteristics within each cluster. Good. Am I making any sense? Good. Yeah. All right. this can be a little bit of this can be a problem actually if you I have to make note that this is unexplained one, which means that if you're starting to including if you start to include predictors to explain the variables, then it's about how much is unexplained for UJs and EIJs. Okay. Yeah, this can be a serious problem because for my master's, I used 3-level models. So the first level was each time, and the second level was each company, and the third level was each business group. And ICC was really low, and then I was hoping that my commute would be too harsh about it, but they were fine with that, but for good reasons. But it can be a little bit a problem if ICC is really low, actually. Any questions so far? Nope. All right. Then I'll bring a new pen, and while taking a 5-minute break, and we'll come back with the STATA exercise combined with different models of HLM.
Within that district. Because all the things, because they exist within a household, there are 4 different CPAs, they're all within that same household income. That's, so within a cluster, the EIJ can't explain the group level, so within a school, individuals can explain the characteristics of the cluster. I guess I was confused what you meant.
First thing that
Wait, would anyone be opposed to turning the heat up like a bit?
variance in the EIJ. EIJ can be explained by the
Okay, yeah, can we turn it up like a tiny bit?
UJ doesn't have any variance.
Thank you.
Okay.
I just didn't want to be that person that
Oh,
turns
right.
it. I grew up when my mom kept the house 75
Oh.
times.
Oh.
And I was like, this is ridiculous. 65.
Okay, so once you get, so within your cluster, you start sampling, the variance of the individuals cannot explain the variance.
Yeah.
Okay,
Like
at the cluster,
beyond the
the
individual.
group
right?
level.
Yeah.
Okay, that makes sense. Thank you.
He was also saying that, like, in that example of the SAT school level SAT score can be
I just wanted to really quickly ask, I'm not gonna ask all of these, but, so EJI in this instance is individual level errors,
Mhm.
and this is
Group
group
level.
level errors? Okay,
Yeah.
and then the DO represents
The grand mean.
the grant, that's right,
Yeah.
that's right, okay. Thank you.
Vice versa, can individual level be careful?
All right. Let's start with the data exercise. Let's go to sections and exercise and download the new file and the data. And the files in your directory and change your directory. Any questions? Nope. Did you? Okay. So the first thing we're gonna cover here is random, oh my God, intercept model. That's to see, but anyways. So random intercept model is about decomposing the group variance in intercepts. So you are decomposing basically each UJ, how the group averages are different. Decomposing Yij into how groups are different on in terms of average and the leftover errors. So we are looking at the relationship between students' SAT score and schools funding. And let's say we have this data. School A and This is school B. Right? And what we're doing here is calculate the slopes based on all observations, but letting the intercepts differ or random, be random. Good. So it'll be like this one. The slope should be same, so it should be looking like this one. And treat these intercepts as random variables. These intercepts are each estimated intercepts, right, for each school, right? But you are letting it as a variable, using it as a variable. Good. And then you are trying to explain this intercepts differences, as well as predicting the slopes as well. Does that make sense? So now, so you're estimating the slopes, right? X variable slopes, right? But they're also trying to explain this group averages differences. So we are playing with more things to explain. Good. I will make start with some notations of multi-level models, but before that, I apologize for that. But it is the notations will be not exactly same as the slides, basically. So before starting, I'll make a comparison between the notations. So in the slides sheet, should be CJ, and then it's B0J, and A is actually gamma 00, and WJ is Z1J, and B is gamma 10, and UJ is U0J, and this one, and G is gamma 10, and K is gamma 11, and ZJ is UIJ. These are the comparisons between the notations, from between the slides and the notations I'm going to use. Good. Did you writing it down?
So why both D and G is gamma 10?
Oh.
D and G.
Oh, D. Sorry. Oh, this is for a random intercept model. And below is random slopes model. Do you want me to speak that, like read that out loud or?
Wait, I'm sorry, what's the bottom right?
This one?
Yeah, the,
ZJ is UIJ.
okay.
Oh,
No, that was one
sorry.
I.
Sorry.
Okay.
U1J actually.
Okay.
If you finish writing them down, no? Need more time or? All good? All good? Okay. So let's consider the case without the predictor. So we are considering the level 1 equation first, where Yij is B0j plus Eij. So it means that Yij is B0j plus Eij. So B0, the intercepts are different across J's. Okay. And for level 2 equation, B0j is gamma 0 plus U0j. So we are making an equation for this one, right? Beta 0j can be decomposed into gamma 0 intercept. So there is 0 because it's about beta 0, right? Does that make sense? And there is 0, this is the intercept for the random intercepts, which is grand mean. And there is U0j because the beta 0j differs by each school. So this is a random term, error term for that beta 0j. Does that make sense so far? Or
You said random error term for the
beta zeros? Yeah. Beta 0j's. Yeah. Yeah. This one? This one is here because it's about beta 0 intercepts. So beta 0 means the intercept for the random intercepts across schools. And composite equation is simple, where you can plug in this right side of the equation into beta 0j. Yij gamma 0 U0j. So this is the composite equation when you don't have any predictors. seems familiar, right? This is same as beta 0 that we talked about. And this is uj that we talked about. We are adding zeros because it assumes intercepts, random intercepts. So I'll explain more why we have more zeros now. Because, yeah, I'll explain more about that in a minute. But the beta 0 that we saw earlier is same as gamma 0, 0, and uj is equivalent to u0j. Good. And let's look at data. So the practice data, I'll explain more about that. So the practice data has some variables. Org ID is organization's ID. And so what we're looking at is whether or the impacts of firm size and gender composition of founders of an organization on a corporation's profitability, which is measured as something called ROE. This is a profitability measure, actually. Okay. So what we're looking at here is these data where each time point for an organization is nested within an organization. Does that make sense? So an organization is a group there, and each time point's values is i's. Does that make sense so far? Or good? And firm size is group level 1 variable because it varies each time. It varies by organizations, but also with time, by time as well, right? Firm size changes. Firm size is measured, by the way, is the number of employees. And gen comp is the level 2 variable where it doesn't change across times. Because this is the gender composition of the founders of the corporation. So, good. And gender composition is 1 for men only, 2 for female only, and women only, and then 3 is mixed gender composition of the founders. Does that make sense? Yeah. All right. So let's look at the first command, mixed ROE, 2 bars, org ID, comma, variance. So the multi-level command for Stata is mixed. It used to be XD mixed, but for recent versions, it's now mixed. ROE is the dependent variable. Okay, and then 2 bars means that denotes the what is the group basically. And then you are entering group ID variable into in full. Does that make sense? So that way, you are letting Stata know that you are running a multi-level model that absorbs uj, which is the average of profitabilities across time for that corporation, for that firm, basically. So you are absorbing uj from yij, each profits from measures for the firm and the specific time. From that, you are absorbing average profitability for that firm. And then running the regression. So as you can see, the results suggest that the number of observations is a little over 4,000, but groups is 65. So it means that there are 65 organizations, and then for all organizations multiplied by times, then you have 4,000 rows, 4,000 something rows. Okay. For example, organization ID. For the first organization, the duration or the times are 73. So it is measured by quarter. So it certified by 73 quarters from the foundation. And then for the organization 2, the data, we have 55 quarters of data. Good. Any questions so far? Nope. All right. And observations per group is minimum is 2 and maximum is 198, because there is an organization that only has 2 quarters in the data, and then there is another organization that has 198 quarters of data. Good. And as you can see, this one is right there. This one is gamma 00 hat. This one, the green. Good. And where's yeah. And variance of this one is variance of, sorry, UJs, U0Js, sorry, U0Js. So this is the intercepts of variance. What does it mean? You are letting random intercepts vary across schools, right? And then you are calculating the variance of intercepts variance, basically. So you have intercepts, right? For all schools, right? So you're using them as data to calculate the variance. You're constructing a new variable, uj, and then or the school's averages, and then you are calculating the variance out of it. Good. So that's 16.86. And variance of residual is variance of EIJ, and that's 84.78. Good. And you can calculate ICC with that information. ICC would be this one. Variance of U0j divided by variance of U0j plus variance of EIJ. Good. By the way, if you type ASTAT ICC, then you can Stata will calculate it for you. So it means that about 16.59% of total variance of profitability can be explained by organizational characteristics. Or 16.59% of the variance of profitability are organizational averages variance. Sure. So 16.59% of total variance of profitability can be attributed to organizational averages. So a couple of FYI thing. I think it's important to know this for your masters, but for this class, in this class, I will let it as a FYI thing. But if you look at log likelihood ratio test right here, then it'll show you chi-square statistic and then p-value. If the p-value is less than 5%, it means it's statistically significant that multi-level models explains more variance than linear models, just without multi-level settings. So it gives some sort of statistical evidence to use a multi-level model. It should be consistent with the ICC, right? They look at the same concepts, but log likelihood test puts it on more of a statistical test rather than just giving you a number, just like this number. How much is explained or not. Any questions?
What is LR?
Log likelihood ratio test. Another FYI is there is a 95% confidence interval right here, but don't use it as an evidence for hypothesis testing. With the null hypothesis of this being 0. Yeah. Oh, standard error. So there is standard errors and then how to calculate it, but this is out of the scope of the lecture or the class, but yeah. Yeah, it's yeah. Yeah. All right. So yeah, again, don't use it as an evidence for the hypothesis testing with the null hypothesis of this being 0. As you might know, confidence interval approach and hypothesis testing approaches are two different approaches, right? They tend to agree upon each other when the null hypothesis say something is being 0 or not. When the null hypothesis something is 0. But in that case, the null hypothesis of this variance of uj being 0 doesn't make sense at all, right? Why is that? Because it should be always positive, not 0. So variance being 0 is there's no every school's average is exactly same, right? But it's really hard to expect that situation. So using this one as the evidence for hypothesis testing is not something you should do. Again, this is an FYI, but just to throw this, let you know. Okay. Let's move on to another model. Let's try to explain things really. Level 1, Yij is beta 0 j plus beta 1 x1 ij plus eij. So you are including x1 variable here. And level 2 stays the same. And the composite equation would be Yij gamma 0 0 beta 1 xij u0j plus eij. Okay. So what we're doing here is, what was the change? Beta 1 and x1, right? By x1 ij, it means that you are including level 1 variable, a level 1 variable in the model, not level 2, right? Because there is i's. So you are trying to explain variance of Ij with x1 ij, right? Then beta 0j will be, say, school averages or organizational averages of profitability after you explain away the variance of Yij with x1 ij. So what we're doing here is you are running the regression, right, of y on x. and then you have errors. And then errors, you're calculating the averages of errors within each organization. Right? And then decompose it to decompose the errors into U0j and EIJ. Right? There should be errors, right? Oh, this is not. No. Oh yeah, that's yeah. All right. So yeah, there might be a. Sorry, this is the right step. So you run the regression, right? Run the regression first of x of y on x, right? Does that make sense? And then you are obtaining errors, right? And you are calculating the average of errors. And then adjust regression line for it. So that's how you can calculate EIJ here. Does that make sense? So U0j will be this amount. U0j hat, to be exact, is this amount. Good. Because the averages of the errors will be about here. So you are adjusting or decomposing these individual terms errors into group averages and individual errors net of group averages. Good. Let's look at the second command. So now we have size variable. So the command is exactly the same, but with size in it. Size's coefficient is that one. Slope, which is interpretation, is exactly the same. And the grand mean or gamma 0, 0 hat is now negative 17 point something. And the beta 1 hat is 0.58. And now, as you can see, compared to the one above, the model above, variance of intercepts or organizational averages is now decreased. And variance of residuals has decreased as well. Because we are explaining away the variance of Yij, both in terms of group level averages and individual errors as well. Right? Any questions so far? Nope. And let's look at the third model. And it's exactly same, but you are um, good. All right. Oh, I forgot to write the proposal. Theta 1 x k plus gamma 1 0 z 1 j plus u 0 j and e I j. Good. Oh, actually, sorry. This should be 0. Did you all write it? Write them down? Good. So the change here is this one, right? Gamma 0 1 z 1 j. So we are explaining the variance of intercepts. Why organizations have different averages for profitabilities. Good. So this is grand mean as all, just like the previous model, but you are explaining the variance of group means with the Z1 here, and there is intercept. Oh, sorry, there is an error or random effects for the second. So this is the fixed effect. This part is gamma 0 1 is the fixed effect, where you are trying to explain group differences. So group differences are explained, right? Some parts are explained. That part is called fixed effects, right? And this remaining group differences is random effects. Good. And as you can see, the command here is exactly the same, but you are simply including this one in the command. So you can explain. You can predict. Interpret size variable. Just like OLS, but for GenCom, you have to interpret the results in terms of group variances, meaning that if an organization's gender composition is mixed, then the profitability or ROE goes up by this one, 2.43. And it's I mean, compared to the groups, the organizations with the male-only composition for founders. Good. Does that make sense? So it should be interpreted as in group terms. Good. Now compare the random effect parameters. Compare these two inputs, right? So before including GenCom variable, the group level variance on explained variance was 9 point something, and individual or time level variance was 56 point something. Now, in the time point level variance has not been changed. It is not changed because we're explaining only the second level variance, group average variance. Good. Does that make sense? And you won't be affected because for every group or for every organization, they would have exactly the same gender composition variable as well. So that's why it won't be affected. Good. And for the variance of U0J is now decreased because group level differences were explained away, some parts of it. All right. Awesome. Any questions so far? Nope. All right. Then let's move on to random slopes model. So far we have only considered variances in intercepts or group means, really. But now we are considering varying slopes across groups. Basically. So it's just like, I mean, it's not just like, but it's sort of like running regressions for each school. Good. And then you are obtaining intercepts and slopes for each school, right? And then you are trying to explain both intercepts differences and slopes differences. Why is there slopes differences? Is what we're trying to explain. Why school B is not really sensitive to school funding increase, whereas school A is. That kind of stuff. So, random slopes model. Level 1 is Yij, beta 0j, beta 1j, x1, ij, eij. And level 2 here is beta 0j is gamma 00 plus u0j, comma. They are different equations actually. And composite. It's we don't have a lot of time, so I won't elaborate more on that. But if you plug in the numbers, then you would have the composite equation. But the important part here is that now beta 1 is not beta 1 anymore. Beta 1j is the new one, which means that slopes according to x variable is different. Did I give you an example of school funding here? Actually, a better example is not that one, but so if you're looking at SAT and then parental income, that would be a great. So why school A has a higher slopes for parental income, whereas school B doesn't have that. Okay. So it's about random slopes model is basically why is there a variance in level 1 variables slopes, not level 2 variables, right? No. Level 1 variables slopes, you're trying to explain that with group variances. Oh, I actually have to write that out. This is important. Sorry. I don't have a lot of time, but it's 1j, 1ij plus uj, u1j, x1j plus eij. So if you write the composite equation, then you can see x1ij has the mean for the slope. So this is the mean slope, right? And then there are variances u1j multiplied by x1ij, meaning that you have mean slope, and then the slope can change depending on the school. Regression slope changes depending on the school. That's what it represents. So now the slopes vary across groups. All right. Good. Yeah. So this is noted as this is the command is mixed ROE size org ID, and you're including size here. So that way you're letting the slopes of size variable vary across groups. As you can see, now you have this part, variance of size, which represents this U1j part. The variance of U1j is 0.0068. Good. And now let's add predictors now, more predictors. Let's say we are explaining intercepts, the random intercepts with C1. Right? So, oh, sorry, gamma. So this is gamma 0j, 1 Z1j, right? So it means that you are explaining random intercepts, varying intercepts across schools with Z1, just like we did in the third model. Good. And the composite equation will be basically gamma 1 C1j. Good. This is represented as the second line of random slopes model. So this is exactly same as the third model that we saw earlier, but with the allowance of U1j. And let's say we are not explaining the random intercepts, but we are explaining random slopes only with Z1, right? Then now it'll become gamma 10 plus gamma 11 Z1j. The slope here, the slopes that vary across schools, is now explained by Z1, which means there's interactions between Z1 and X1. Good. So it is represented by this line, mixed ROE size gen comp. All right. And the last one here is when you explain both the intercepts and slope with Z1. And the composite will be our gamma 00, gamma 01, Z1j, and the rest is same. It will be just like the last line here, And as you can see, you can also see the main term, not just the interactive Gen computer. All right. So I have a couple of topics left, but they are all FYIs, rather than you need them for problem sets and stuff like that. So I'm happy to talk more about that if you're interested in any other topics. And for panel data ones, it'll be covered at the end of the semester. So don't worry about it. Won't worry about it. And yeah, I think that's it. All right. Then I'll see you tomorrow in lecture.
간단하게 내가 잡으면 네 그렇게 좀 약간
네. 조그만 크게 한데 테스트가 안 돼가지고 말씀드렸어요.
작은 게
네네. 미터.
Ready? Oh yeah. 2 years of hair. Wow. Yeah. Thanks.
British.
I'll see you later. Bye. man.
You're British. Substantially a braver. No. Well, I'm glad you